Then moving on to the main profile. This was originally intended as the profile for meeting the needs of most broadcast and storage applications such as Blu-ray and broadcast TV. The emphasis here was very much on coding efficiency, so we are within the main profile starting to bring in the higher order coding tools where we can actually achieve much higher levels of compression, approaching the 50% range that we saw on the original specification requirement of H.264. However, to achieve that level of coding efficiency does mean that we need to apply more computational power, and therefore we add latency. So we're not, generally speaking, using non-real-time encoding here. It's important to note as well there that the main profile has really receded in interest following the work that was done with the frequency range extensions, which I'll be talking to you about later. And then the final profile of the original three as defined by H.264 is the extended profile. This has, again, similar to main, it has high compression capability. It also adds some extra trick tools there to provide extra robustness in varying network environments. And it also includes the robustness of the baseline profile. So we get the best of both worlds in terms of baseline and main. We get the improved coding efficiency of main and the improved robustness for network transmission of baseline. But again, because of the work done on the frequency range extensions, then the extended profile has waned in popularity in favour of the high profile of the FR extensions. Which then takes us on to the needs of these Fidelity range extensions within H.264. So the initial work that H.264 concentrated on was primarily of entertainment quality for either disk or broadcast use. And it didn't really look at the professional video markets for where the information is being originated for film production and so on. So the original profiles that we had there were limited to only 8 bits per sample, so one of 256 levels, and the colour sampling was limited to 420 as a colour space map. The frequency range extensions produced in 2004 allowed for the use of very high bit rates to achieve very high definition video streams. It also used higher level coding efficiencies, using some high-level coding tools, and again, in this particular case, using the frequency range Fidelity range extensions allowed us to actually achieve compression of 3:1 over MPEG-2, so exceeding even their original goals. It was also possible with the Fidelity range extensions to achieve even lossless video, going to very high bandwidths and so on. So that defines really where the Fidelity range extensions came from and the requirements which the applications they fulfill. So the high profiles themselves, the 4 high profiles comprise of the high profile itself, and this is the one that's the primary source and technology used within Blu-ray discs, for example. So it is 8-bit video and again 420 colour sampling. The high 10 profile then takes the sampling rate up to 10 bits per sample, but again it's limited to a 420 colour space. 422 takes us to 10-bit sampling, but 422 colour sampling, so we get higher colour resolution. And then finally we have high 444, which gives us 444 colour sampling and up to 12 bits per sample, so very high quality recording there achieved through H.264 high 444 pp. What does that mean then in terms of the processing power required to compress H.264 streams compared to MPEG-4 Part 2? Well, the improved compression that is achievable through H.264 does require far higher levels of computational power and therefore cost. H.264 is, as we've seen, a much more sophisticated and much more complex compression method, and so therefore it's going to take significantly more processing power compared to MPEG-4 Part 2. And to quantify that, then, to encode like-for-like streams of resolution and bitrate and so on requires approximately 3 times the processing power for H.264 compared to MPEG-4 Part 2, and that's only using the baseline profile of H.264. Remember that only achieves a 20 to 30% reduction in bit rate or storage requirement. So it takes 3 times the processing power to achieve a 20 to 30% reduction in bit rate. Similarly, at the decoding end, when we're decoding our H.264 stream, again baseline, comparing that with MPEG-4, again takes 3 times the processing power approximately to do the decoding, to do the rendering onto the screen and so on. So that means then that in many centralized recording solutions using NAS as the storage method, then it's going to force us to be using very high power and therefore very expensive PCs to achieve realistic levels of performance that we achieve in today's CCTV systems. And that's going to add significantly overall to the system cost. Also, going to PCs can introduce system reliability issues, maintenance issues and so on, and also security issues with the level of protection we need to apply to our PCs. H.264 then certainly shouldn't be seen as a panacea curing all ills, and many of the features of H.264, although very, very useful in an entertainment environment, offer very little benefit when we're encoding or decoding CCTV images. For instance, if we look at multi-picture inter-picture prediction, it's very, very useful in back and forth motion, which will be applicable in films and so on, but it provides no benefit at all in a CCTV application. It's far more important in real CCTV systems to be able to generate multiple streams, and those streams should have parameters designed to suit the connectivity that exists between the client, the viewing operator, and the server, the digital video recorder or whatever. So the ability to generate multiple streams simultaneously, both for viewing live and playback, and to be able to transcode images from one stream to another, is really far more important to provide real benefits to real CCTV users. Also, we want to seamlessly integrate the various image sources that we have available to us now within CCTV. So that would be standard analog cameras, standard resolution IP cameras, and megapixel recording. We want those to be seamlessly integrated onto the one viewing platform, the one recording platform, so we can actually switch from camera to camera to camera without wondering or concerning ourselves with what kind of camera it is by going to a different platform to view the megapixel cameras, for instance, on a PC. Also, we don't want to use PCs for decoding. It would force us to use high-powered PCs, which would add significantly to a system cost. It will, generally speaking, not give us a seamless solution. And as stated previously, it raises security issues, reliability issues. It's far better for a number of reasons to actually have a fully embedded solution.